Welcome back, everybody. This is Brandon Davies from TRC, and today we're going to be going over our final day on transmission line protection. We'll be covering a high-level overview of transmission line pilot protection schemes. All right, so our agenda for today is to do a quick recap of days 1 through 3 and specifically talk a little bit about the step distance schemes that we've been discussing and some of their limitations and reasons why you might move to doing something a little bit more complex, such as application of a communication assisted pilot type scheme. Really, these schemes are leveraging a communications channel in between the two terminals to allow you to gain some increased reliability and operate speed at the kind of cost of some extra complexity. So we'll be taking a look at different types of pilot schemes, directional comparison schemes, including blocking and permissive type schemes, and also, take a look at line current differential, which is a type of scheme that's being used more and more by utilities these days as the communication infrastructure is updated to support it. We'll be taking a look at different types of pilot communications channels, and then also some application considerations of some things you might have to look out for when applying a pilot scheme for a transmission line. So we've gone over these protection system objectives in the other classes, but again, we're going to try to relate our discussion of pilot schemes and the reasons why we'd apply them, why they may be considered a better fit for an application in these terms. So I did want to highlight this again. There, really we're looking at reliability, balancing the security and dependability of the scheme. Selectivity, making sure we're operating for the appropriate faults, that we're really minimizing the impact of the service disconnection. Speed, so we want to operate as fast as possible, and that's one of the big benefits of pilot schemes is you do get an increased operate speed of your scheme. Simplicity, so this is maybe one of the slight drawbacks of a communication assisted pilot scheme, is that the scheme itself becomes more complex. You're dealing with information being shared between relays, communications channels. So that's maybe one of the drawbacks of these types of schemes. We'll take a look at some of the considerations for that as well. And then economics, obviously, so if we're having more complex schemes, we have different communications channels, maybe more complex relays, there's going to be some costs associated with it. So we'll kind of frame all of our discussions about these pilot schemes, kind of trying to relate back to these protection system objectives wherever possible. So I also wanted to highlight some of the definitions that we talked about when we talk about pilot schemes and the protection elements we're using within these schemes. We're going to be using a lot of the same terminology we did on the step distance scheme, where we'll be looking at overreaching and underreaching elements, elements that are set to either look past the end of the line or set in a way that we can be sure that they're not going to reach the end of the line. And we'll really be doing a lot more with forward and reverse elements. So again, from the relay's perspective, with a typical connections, forward is considered towards the protected line, and reverse is towards the system behind the line terminal. And that same applies at either station, either end of the line. So we'll use those terms to really describe how we're making a more informed decision by using directionality at both terminals to make a trip decision. So over the last couple classes, we've really been focusing on step distance protection as a scheme, and that's a widely used type of line protection scheme, largely due to its simplicity and ease of application. We're looking at terminal by terminal, so we just have a single relay at each terminal that's set in a way that by using a mix of time coordination and sensitivity coordination, we're able to protect the full transmission line for faults, with a good portion of it, often more than half of the line, protected instantaneously, with no delay from either end. And the rest of the line having a short time delay to allow coordination with other area relays that may operate instantaneously. So that's a pretty commonly applied scheme, but it does have some drawbacks. The main one being that there's cases where your system criteria and your protection criteria for that part of the system dictates that you have to operate faster than what that zone 2 delay would be. And that could be due to a system stability issue or other critical clearing time requirements. And that drives a need for a more complex scheme that will allow you to operate instantaneously, ideally for the entirety of the transmission line. And that's where pilot schemes come in. So, oftentimes we're using the same protection relays for our pilot schemes as we would for the step distance protection. But the main difference between those is we're using a communications channel between the two substations to share information from one relay at one terminal to the relay at the other terminal. And the type of information shared varies by scheme, but in general, we're sending a very small amount of information that can allow both relays to make a more informed decision if the fault is within the protected line section or outside of that line section. So depending on the type of scheme we apply, we're going to have different communication requirements as well. Many historically used schemes, your permissive or blocking schemes that we'll talk about, really just need one piece of information. The relay needs to know if the fault is on the line or not, as seen by the other terminal. Some of the more advanced schemes, like differential schemes, line differential, requires a little bit more of a robust communication path. And there's a lot of different options out there that utilities will use for these communications channels, and we'll talk a little bit more about that. Generally, as I mentioned, you're using the same relays and you're applying these pilot schemes within the same device as your other protections, such as your directional ground overcurrent protection, your step distance scheme, switch on default protection. With modern multifunction relays, you're really able to apply all of these schemes within the same device, which certainly cuts down on the complexity of the wiring and connections to the relay, and then gives you a lot of flexibility in what you're applying for your scheme that you're trying to accomplish. So we can break down the types of pilot schemes into a couple different categories. The first is a directional comparison scheme, and this is using directionality in the relays at either terminal to tell if the relay is in front of each relay, or behind each relay, or a mix of the two. And those generally can be broken down into permissive schemes and blocking schemes. So a permissive scheme basically would be a relay at one terminal saying, hey, I see the fault in front of me. I'm giving the remote terminal permission to trip fast if it also sees a fault in front of it. The blocking type scheme is kind of the opposite. You're looking for is there a fault behind this relay terminal, yes or no, and they're sending that to the other end to prevent that other relay from tripping high speed on the pilot scheme should that happen. We'll go through a couple examples of those. There's also some direct tripping schemes, like a direct underreaching transfer trip scheme, that one relay at one terminal can directly trip the breaker at the other terminal through the communications channel, and oftentimes processed through the relay logic. The other main type of pilot scheme is a differential scheme, and there's a couple varieties of this. There's a phase comparison scheme, which is a older technology that it really isn't widely used anymore. And really, the ones we're seeing these days is a true line current differential scheme where both relays are measuring currents into their terminals, and then they're actually sending those real-time values of the measured current to the remote terminal. So it not only knows what current measurements are happening at its instrument transformers, but also knows what's going on at the other terminal. So we can do some more advanced differential type protection schemes with that we'll talk about. But any of these schemes are going to require some type of a communications channel between the two line terminals. And oftentimes when we're talking about transmission lines, these terminals may be tens or even 100 plus miles apart. So we need some communication infrastructure to span that distance and be able to provide high speed, high reliability type communication from one terminal to another. As I mentioned, many of the schemes, you really only need to send one bit of information. We need to say, hey, does this relay see a fault in front of it, yes or no, or see a fault behind it, yes or no, which simplifies that quite a bit because you're able to really choose your communications channel, and you really don't need a lot of bandwidth to send that information. Communications requirements get a little bit more complicated when we start talking about line differential and other more advanced types of schemes. But in general, we're able to use some pretty basic communications techniques. So some of the common pilot communications channels is a least line audio tone. So this would be like a least phone line. We're seeing that less and less over time. That's been something that utilities have been moving away from as the phone infrastructure has changed from analog to digital technologies over the years. Another is power line carrier, and I've got a couple example waveforms over here of an on-off and a frequency shift keyed type carrier signal. And that's basically using the conductors of the power line, the transmission line itself, to carry a high frequency signal from one end to the other. So that's really commonly used type scheme, especially 10 to 20 years or more ago. That was a very, very commonly used scheme because all the infrastructure is there as far as the mechanism to get it from one terminal to the other. There are some other equipment located at the substation that you have to apply, but it's a very convenient way to send that information from one end to the other. More commonly these days, we're seeing a lot more utilities move towards installing fiber optics on new transmission line installations. So I think I mentioned in the first class that and showed a picture of a optical ground wire. So when you're putting up new transmission lines or you're refitting old transmission lines, it's pretty common practice to include fiber optics in that design, one of those OPGW ground wire configurations. That allows you to either provide a direct fiber connection between the two stations, or you can utilize some of those fibers in a SONET multiplexer network that allows you to provide communications between multiple nodes within a larger communication network, again with a focus on high reliability and high speed. And then lastly, microwave is another technology that's been used widely over the years. You'll see some of these microwave towers at various locations and substations, and it's just a different mechanism of sending those communication signals across long distances. So I think one of the best ways to really get a good understanding of how different pilot schemes work is to really take a look at the scheme logic, what's going into them, and then seeing how that logic operates or doesn't operate for both in-section and out-of-section faults. So we're going to go through a few different pilot schemes, and we'll take a look at it from that perspective, go through examples of in-section faults, what the relays are seeing, what elements assert, what communication channels send what information, And in the end, how the end decision is made to operate or not operate for that given fault. So the first type of scheme we're going to look at is a permissive overreaching transfer trip scheme. So a couple key words there is permissive. That's the type of scheme. In a permissive scheme, you've got a relay at one terminal telling their other terminal that they have permission to trip high speed if they see a fault on the line, because the terminal that's sending the permissive signal sees a fault in front of it. So it's, a lot of these schemes are going to operate on the same basic principle of, if you see a fault in front of you, you send that information to the remote terminal to allow that terminal to build that information into its trip decision. If you see a fault that's out of section or one that's behind you, you'll know that the fault is not on your line. You won't send that permission. The other terminal will have to wait to make a trip decision based on one of the other schemes that's being applied, and the pilot scheme won't operate. So basically, the simple POTT, or permissive overreaching transfer trip scheme like this, uses overreaching protection elements, and this would be a combination of phase and ground, distance elements, or ground overcurrent, directional ground overcurrent elements that look onto the protected line from either terminal. So you can see we've got the two R0 reaches here. Those are your relay overreaching zone. You can see they look past the end of the remote terminal. And they're looking in the forward direction onto the protected line. So just looking at this, you can tell if both of those zones are picked up, both of those overreaching zones are asserted, the fault has to be on the protected line, because the zone is only going to pick up for something in front of both terminals. In process of elimination, if we know the fault is in front of both terminals, we know it must be on the line. So we can use this to provide high-speed clearing for the line for the entire length of the line, unlike a step distance scheme where we're going to have some portion of the line with a time delay on it, by sharing the information about this forward overreaching zone from one terminal to the other. And that's done through the communications channel shown on the bottom of the figure, where we've got a transmitter and a receiver shown here. So the basic trip logic for this says that if the relay at terminal 1 sees the fault in front of it through that overreaching zone and is receiving permission from the remote terminal at terminal 2 through that communications channel, then we'll trip the circuit breaker. And the same thing will be happening at terminal 2. We'll be using that same logic, and assuming the fault is in section, both AND gates will be satisfied, and you'll trip both breakers. So if we take a look at this for an in-section fault example, we start out with a fault occurring on the protected line. So this is somewhere midway through the line, though the scheme would work for anywhere within the protection line protection zone. And the local relay elements assert. So you can see I've got highlighted up here both overreaching elements will see the fault because it's within their reach. And down lower, I've also got highlighted the logic functions that that remote overreaching or the relay overreaching element asserts, and that goes into the scheme logic. So you can see the trip decision isn't made at this point because we're waiting on the receipt of the permissive signal from the remote terminal, and we haven't gotten that far through our logic yet. So because the transmitters at each terminal are receiving a instruction to send that permissive based on the local overreaching element, they both send a signal to the remote end, and the receiver at that end asserts to indicate that it's received the permissive signal. At that point, the logic within the relay at each end, the AND gate associated with the trip function, um, they both are now satisfied because both inputs, both the local overreaching element and the permission are received, and that operates to trip both circuit breakers, and that will clear the fault, and the line can then reclose or do some other type of operation to tell if the line can be re-energized at that point. So if we look and do the same thing for an out-of-section fault example, we want to make sure that we're not tripping for an out-of-section fault case. So if we say that we've got a fault at the bus of terminal 2 here with circuit breaker 2, and we can see that only one of the terminals sees that fault within its protected zone. It's out of zone or out of the operate region for the station 2 relay is not going to see that fault as within that forward overreaching zone. So the relay at terminal 1 does see the fault, and you can see I've highlighted the section here going up to the AND gate, though that's not satisfied yet because we haven't received a permissive. And we're highlighting down to the transmitter, meaning that the logic within the relay is going to key a permissive signal to the remote end. When it does that, the receiver at the remote end is going to receive that and use that as part of its scheme logic. And when that's processed, you can see the AND gate on the terminal 2 side is not satisfied because even though we are receiving a permissive, the relay at that terminal doesn't see a fault within its forward overreaching zone. So no trip decision is made. In both cases, the AND gate for the trip logic as part of this POTT scheme is not satisfied for this out-of-section fault. And that's how you gain the security through this scheme. You can still operate fast, but you're securing the elements that you're using that additional information from the remote terminal. A variation of the permissive overreaching transfer trip scheme is the permissive underreaching transfer trip scheme, or PUTT scheme. So it operates on a very similar principle as far as one terminal sees a fault and provides a permissive signal to the remote terminal, indicating that that terminal has permission to trip high speed for that fault. But rather than using an overreaching element for that, it is going to use an underreaching element. So you can see up at the top here, I've got two elements on each terminal, an RO, or my overreaching element for that relay, and an RU, which is an underreaching element. And the scheme is going to operate in a way that the underreaching element, similar to a step distance scheme, will trip the local breaker directly without receiving a permissive signal from the remote end. The overreaching element is going to require the receipt of the permissive from the remote end, and those two are going to work. Those two parts of the scheme are going to work together to provide 100% coverage for the entirety of the line. So the best way to go through this may be just going through an in-section fault example. So if we start out, we've got a fault occurring here near the terminal 2 location. We can see what elements out of the scheme are going to see this fault, and we can see that both terminals overreaching zones are going to operate, and the underreaching zone, the forward-looking underreaching zone at terminal 2 is going to see that, which is the top RU here on this diagram. So if we start by looking at terminal 2, we'll see that both of the elements have operated. And if we highlight the logical path there, you can see that the RU element is going to this OR gate. Because it's an OR gate, it passes right through that and goes up and operates the contact to trip circuit breaker 2. The underreaching element is also used as part of the permissive signal, so you can see that's going over to the transmitter. The overreaching element's going down here to the AND gate, and that's what's going to operate if the permissive is received. And right now that AND gate is not satisfied because we're not showing a permissive signal being received for this terminal yet. If we take a look at terminal 1, you can see that the underreaching element is not operating. So the underreaching forward-looking element is not set long enough to see the fault because it's too close to the terminal 2. But the overreaching element does see it. So the overreaching element asserts and goes to that AND gate. The AND gate's not satisfied yet because we have not received a permissive signal from the other end. And as the signal's transmitted from the appropriate terminals, we can see that AND gate does get satisfied because we've received a permissive signal from terminal 2. We're seeing the fault in front of us, and because that condition is satisfied, the logic goes through the OR gate up to trip circuit breaker 1. And you can see because the underreaching element at terminal 1 never asserted, that permissive was never sent from terminal 1 to terminal 2. So the AND gate associated with the overreaching element at terminal 2 never asserts. But that's okay because the underreaching element at terminal 2 has already operated to trip that breaker. So once the trip decision is made, both circuit breakers, breakers 1 and 2, are both tripped, and the scheme has made an appropriate trip decision to clear that fault. So this scheme obviously has a little more complexity than the basic permissive overreaching transfer trip scheme, but it also improves security in a couple ways. Mainly because the only conditions we send a permissive for are those that are in section faults. So if we have a fault that's on the remote bus, an out-of-section fault, neither terminal is going to send a permissive signal. So that there's some security advantages to that type of scheme, though it's pretty minimal, and we don't really see a lot of utilities opting for a permissive underreaching transfer trip scheme over the permissive overreaching transfer trip scheme, because the difference in complexity of this scheme versus the difference, the increases in security, kind of they generally don't. The added complexity isn't something that warrants that unless you've got a specific scenario or a very critical terminal you're trying to apply this pilot protection for. So one of the other very commonly applied pilot schemes is a directional comparison blocking scheme. And this operates on somewhat the reverse principle of the permissive scheme that we just talked about. With the POTT scheme, one terminal is telling the remote terminal through a communications channel that it sees a fault in front of it. So if that terminal also sees the fault in front of it, it must be in section, and that terminal can trip. The blocking scheme operates on the opposite principle, that the relay is monitoring for faults that are out of section, faults that are in the reverse direction from the line. And if it detects a fault that's out of section, it sends a blocking signal to the remote terminal telling the remote terminal not to trip, even if it sees a fault within its forward overreaching zone. So this scheme is going to operate very similarly, that you're going to have a communications channel that's sending that single bit of information, in this case a blocking signal, to block or not block. Those are really the two options. Um, and that's going to be driven by a couple different um, protective elements. So we're similar to the POTT scheme, we're going to be using one of the relay overreaching elements set to see past the remote end of the line. But we're also going to provide a reverse looking element that's going to be set to determine if the fault is behind the relay. So for each terminal, we'll have that forward overreaching element and the reverse blocking element. When we set this scheme, you can see that the line, the dashed line for the blocking element shown in B, shown by the letter B, is longer than the overreach of the overreaching element from the remote terminal. And that's done intentionally, that you want that blocking element to be set more sensitive than your remote overreaching element, so that you can be sure you're going to apply a block for any scenario that the relay is seeing a fault in the reverse direction. If the overreaching element happened to reach longer than your blocking element, there'd be certain faults that you would not get the block and you could potentially trip for. So that's one of the things we'll coordinate when we're doing our protection calculations for this type of scheme, and is really built into how we go about applying this. So we'll jump right into an in-section fault example here. We start out and we have a fault occurring on the protected line, similar to the analysis we did on the last example. First thing we'll see is that the local relay elements will assert to say that they have detected a fault within that forward overreaching zone. And that's shown here, the zones highlighted, as well as the logic within the relay being highlighted as well. And you can see this is going into an AND gate with an inverted input based on the receipt of a block from the remote terminal. So with just the overreaching element asserting and no block present, so the other portion of that AND gate is satisfied, the output of the AND gate will assert, and that will drive a timer, our blocking coordination timer, shown as TL1, and that's going to start timing. So because we have to wait to see if a block is received, we have to delay the scheme slightly, and this is usually 2 to 3 cycles, so it's a very short delay, even compared to some of our other scheme delays for like the step distance scheme. It's still a very high speed type of protection. So for the in-section fault, this timer is timing and it's waiting to receive a block. And if a block's received, the timer will drop out to prevent a trip from happening for an out-of-section fault. But in this case, the block is not received. So even though the scheme is timing, we don't receive a block. And once the blocking coordination timer times out, the trip decision is made. So after the fault, a few cycles later, we've now made a trip decision to clear the line for this in-section fault. And each terminal trips its local breaker, and the fault goes away because we've de-energized the faulted portion of the system. So if we look at that same system for an out-of-section fault example, we can see how that blocking signal comes into play in making the trip decision for the line, or the no trip decision in this case. So if we put a fault in that same location at the terminal 2 bus behind the relay, we can see that the terminal 1 overreaching element sees the fault. It's within the reach of that overreaching element. And the terminal 2 relay sees the fault in the reverse direction because it's behind the relay, with the kind of demarcation of forward and reverse happening at the CT location. So it's seeing this as a reverse fault. And the appropriate elements will assert on each terminal. So you can see at terminal 1 here, we've satisfied this AND gate because we've received the overreaching element, and we're not currently receiving a block, and the coordination timer starts timing. So this is timing, waiting for the block to be received. At terminal 2, the blocking element is asserted, and we're sending that to our transmitter. The appropriate signals are transmitted and received. So in this case, we're only sending a block from terminal 2 to terminal 1. Once the receiver receives that signal, it applies a logical 1 to that inverted input to the AND gate. Because it's now receiving a blocking signal, the output of the AND gate drops out, and the coordination timer, TL1, resets and drops back out. Because the block was received and prevented the trip at terminal 1, we're not tripping that terminal. And because the overreaching element never asserted at terminal 2, we're not tripping that terminal. So again, this scheme logic has provided a correct trip decision that it's not going to operate for that out-of-section fault. So the next scheme we're going to take a look at is a direct underreaching transfer trip scheme, or DUTT scheme. And this scheme operates in a similar way that we're sending a single bit of information from one terminal to the remote end, but operates on a little bit of a different principle, that we're directly sending a trip signal from one terminal to the other terminal when that terminal sees a fault that it knows is an in-section fault. So we're not waiting and conditioning that with anything on the receiving end. When the receiving relay receives the DUTT transfer trip signal, it's going to directly trip the breaker regardless if the local relay sees a fault or not within the appropriate zone. So this type of scheme really has to be used in conjunction with at least the zone 1 portion of a step distance scheme, because we're going to need to be able to trip instantaneously for a fault that's close in that the remote terminal may not see in its underreaching element. So for our communications channel, we're sending that single bit. For our relay elements used in this scheme, we're only looking at an underreaching element. So these are the elements that are going to see only a percentage of the way down the line, and they're not going to be able to detect faults at near the remote terminal. So that's why we really have to have that step distance scheme, or at least as the equivalent of a zone 1 instantaneous direct tripping element for the DUTT scheme. So for our in-section fault example, we've got a fault that is near this circuit breaker 2 position here. So we're going to have some local elements that will assert. So you can see that the terminal 2, it's a close in fault. It's within the underreaching zone associated with this scheme. And that's going to assert, and it's going to go through this OR gate and trip the local circuit breaker. At the same time, it's going to go over to the transmitter and send a direct tripping signal to the remote end, telling that circuit breaker to trip as well. You can see that the underreaching element, the element at terminal 1, is not asserting because the fault is occurring beyond the reach of that element because it doesn't cover the entirety of the line. So there's really no fault detection going on at terminal 1. So terminal 2 transmits the transfer trip signal, the underreaching transfer trip signal to terminal 1. And because the receiver there isn't doing any kind of local conditioning with that signal, it just goes right through the OR gate, and that asserts to trip circuit breaker 1. So you can see from that logic, both terminals clear or trip to clear the fault, and the relay has made a appropriate trip decision based on the in-section fault. I'm not going to go through an out-of-section fault example on this one in detail, but it's fairly straightforward. If you had a bus fault at either of the buses, neither of the underreaching elements is going to see the fault. So none of the protection related to this scheme is going to detect the fault at all, and none of the logic will process. So this has some advantages in that simplicity, but may not be as robust of a scheme as the permissive overreaching transfer trip or the directional comparison blocking scheme. So oftentimes we don't see this scheme used as a primary pilot scheme for a transmission line. Usually either the POTT or DCB schemes would generally be the choice that the utilities would make. So the last type of pilot scheme we're going to talk about today is one that's really starting to be used a lot more commonly on the transmission system, primarily due to the increases in availability of a more robust communications channel, and that's line current differential. So the other schemes we talked about, the communications path, really just had to support a single bit of information. You're either sending a permissive signal or a blocking signal or a direct tripping signal, but it was just a single bit of information. And each of the terminals would receive that information and use that in conjunction with local relay elements to determine if the fault was in section or out of section, and if the scheme should operate. Line current differential operates on a different principle, and that's a differential principle. And instead of sending that single bit of information, we're actually sending measurements from each terminal to the remote terminals. And those current measurements are used to, in conjunction with the local measurements, to calculate a differential current for the transmission line. So differential current can be thought of as basically Kirchhoff's current law. Current into one phase of the line has to go out the other phase of the line. So those currents have to sum to zero. And if they don't sum to zero, then there's some other path for that current to be flowing. And that path would generally be a fault. So it operates on that principle that if the currents into the line aren't equaling the currents out of the line, there must be a problem and we should operate. It's not quite that simple because there's a few other things that we have to consider: measurement errors, communication delay errors, CT accuracy errors, and saturation performance if there's the CTs aren't operating and providing an ideal output. So there's some other things that go into that differential principle that are used to secure that, and obviously there's a lot of communications requirements and things that have to be considered that go into the scheme. But in the end, the base functionality of any differential scheme is that the current going into a protected zone has to equal the current going out of the protected zone, and if not, make a trip decision based on that. So for our line current differential scheme, our relay at terminal 1 is measuring currents, processing those, time-stamping them, and sending them to terminal 2. Terminal 2 receives the currents and then aligns them with the local measurements to make sure that they're in sync with one another as far as the communications delays and times. And then the relay takes those two currents and sums them together to create a differential current. And that differential current's our operate quantity that we'll use for making a trip decision. During a normal operating, when there's no fault on the line and there's not significant errors, those currents should sum to be zero. So your differential operate quantity would be zero. When there is a fault on the line, like I've shown here on one of the phases, the currents no longer equal zero, and they'll sum together to be the fault current. So that's one of the reasons differential protection is popular when we're able to apply it. Is our the difference between our normal operating measurement for our operate quantity, which in this case is normally around zero, and what we have for a fault is very different. We're going to go from seeing basically no differential current up to seeing a very high magnitude of differential current. So we can make a very secure trip decision based on those measurements, assuming we don't have other major sources of error. So, when these more robust communications channels are available, and that would typically be your direct fiber optic communication, either directly on the transmission line or through some other path, or through a multiplexer network that shares information between multiple terminals. When that's available, line differential is a really popular choice for utilities. And a lot of utilities are really focusing on building out that communications infrastructure to be able to provide that type of scheme and some of the other benefits that come with having a very robust communications architecture for their system. So a couple things about this, one is you really have to be careful with your relay types. You can't take a line differential relay from one vendor and apply it at one terminal and another from another vendor, or even just a different model from the same vendor between your two terminals. So there's some additional coordination in the design and specification of the equipment that goes into applying a line differential scheme. And then you have to make sure the firmwares and the applications really line up, and that when you're configuring the relay at one terminal, you have to understand the other terminal as well. So things like the current transformer ratios and some of the other settings have to be shared between the two terminals. The line differential scheme also oftentimes includes some additional features to compensate for unique scenarios. Things like compensation for line charging currents, which could be another source of error. In here, you've got the capacitance of the line, which will have some amount of current draw, even when the remote terminal is open. And there's some logic that can be applied within many of these types of relays to compensate for that effect. If you know what the capacitance or susceptance of the line is, you can set the relays to kind of cancel that out of the active measurements going into that differential calculation. You also have to be really cautious if you're applying this and there's a tapped station or a multi-terminal line. If there's something like a tapped transformer, even if it's just feeding loads, you still have to be cautious because this differential scheme can be set very sensitively, and you may be in a situation where a fault on the low side of a tapped transformer or some other part of the system may may trip when you don't want it to. So you got to provide a little extra care when you're applying this type of scheme, and there's some of those other unique scenarios going on. But overall, the line differential is a great option. Operates high speed for the whole length of the line. Is really able to have a lot of sensitivity in differentiating between in-section and out-of-section faults. And it's really just a great choice overall if you've got the communication infrastructure to support it. So this slide has a high-level summary of some of the considerations that go into selecting a pilot scheme and kind of a general comparison of some of the pilot schemes we've talked about, as well as some other types. Really highlighting some of the reasons we, may opt for one scheme over another. So you can see I've got some columns here for speed, the channel requirements, security, dependability, and simplicity. And really the star ratings off to the right on those columns, that's just kind of my own personal opinion about these schemes. So just because something has 4 stars over 3 stars versus 2 stars does not mean that that there's some major problem in applying one scheme over another. It's just there's some very nuanced things that there might be some advantages, slight advantages in security or dependability or simplicity. So if we look at these, you can see that when we're looking at the speed column, in general, all of our schemes are operating very fast. If you recall, our time delay for our step distance scheme was something in the 18 to 30 cycle range, so between 0.3 and 0.5 seconds to operate. And these schemes are generally providing a trip decision within 2 to 3 cycles. Some of them potentially coming in even faster than that, less than a cycle in some instances. So generally, they can all be applied in a case where you really have high speed requirements for system clearing. The channel requirements here, we've got most of these schemes are just transmitting a single bit. And there's some differences in the channel reliability. So certain types of communications channels, such as power line carrier, may be interrupted during a fault. And if you're trying to send a permissive signal through a channel that's interrupted when the fault's on the line, that might not be ideal for that case. So if you've got something like a carrier channel, you might be more likely to choose a blocking type scheme, such as the directional comparison blocking scheme, because that only needs to send a bit through the channel when there's a fault that's an out of section fault, because it's a blocking type scheme. So we've got some of the things listed there for some of those considerations. And then lastly, the 87L is going to be the one that has a much more robust channel requirement, and generally that's a 64 kbps type channel, and the channel needs to be uninterrupted when there's a fault. So that's generally less of a concern, for that type of channel. That's really more of a concern for carrier signals and things like that. But in general, it's going to have a much higher communications channel requirement. Where we're looking at the remaining 3 columns of security, dependability, and simplicity, a lot of that's going to be a very fine balancing act between those requirements. In general, any of these types of schemes can be applied, with a focus on security and dependability, the overall reliability. And then lastly, the column having to do with simplicity really just comes down to how complex the scheme is. And generally, the more more complication, more complexity you add to the scheme, the higher the likelihood is that you're going to misapply the scheme or not consider something and potentially have the scheme not operating as intended. So I just wanted to put this up here to kind of compare and contrast why we may look at one scheme over another. And really, a lot of utilities have requirements and criteria they'll provide that will help help make these decisions based on their knowledge of their own system and other input criteria that would go into your scheme selection. So I also wanted to highlight a few general scheme considerations. So the first one is cutoff switches. So generally, when you're applying a pilot scheme, you're going to want some way of turning that scheme on or off. Generally, they'll just turn off the pilot portion of it and leave some of the backup stuff like your step distance scheme or directional ground overcurrent schemes enabled. And generally, this would be a control switch or a digital push button on the relay that would disable the tripping functionality of that scheme. And that can be accomplished either with a single scheme that just turns everything on and off, or a scheme where you're turning transmit and receive off separately. And the status of those switches may be sent over a communications channel to the remote end, so that the remote end knows when the scheme's disabled at one at the other terminals, and can make logic changes to the scheme to accommodate for that. So that's generally something you'll see. That way, if there needs to be maintenance on the communications channel, or there's some other something else going on at one of the other terminals, you can disable the scheme temporarily and then put it back in service once that work is complete. Generally, we're looking to provide some channel monitoring. So obviously, these schemes all rely heavily on the communications being available. So generally, we're providing some kind of channel monitoring and alarms that will say there's a problem with the communications channel. That way they know they can get somebody out to fix it. It also impacts our maintenance testing intervals. So generally, when we're applying the scheme, we're thinking about channel monitoring as part of that package, so that we understand when there's a problem and can go out and have someone go out there and fix it. Redundancy requirements. So again, oftentimes in the transmission system, we're providing redundant systems. So we'd have 2 relay packages at each terminal, providing protection for the line. As we get into higher voltage systems, sometimes there's more requirements and compliance requirements to provide redundancy in the communications channels for those pilot schemes as well, so that there's not a single point of failure. So if you have a communications outage on one system, your other system will theoretically be available to provide high-speed clearing through that redundant channel. Some schemes, such as line differential, you can also provide redundant channels on a single relay as well, which has some advantages. That way you can disable one of your channels and still be able to have the scheme operate as intended if you had a communications channel failure on one of your redundant channels into that relay. We've also got some pilots channel selection requirements. So there might be some unique things you'd look into if you have a weak part of the system where you're applying the scheme, and some line length considerations like the SIR topic we discussed as part of the step distance scheme. Pilot schemes can be applied to multi-terminal lines. So the examples I provided today were 2 terminal applications, but they can be applied. The same principles can be applied for many schemes to multi-terminal lines. Obviously, you have some additional analysis and additional complexity added to the protection scheme, but most of them can be adapted to accommodate that. Another consideration is that once you have this communications channel between the relays, you may be able to leverage it for some other uses. So pretty commonly, we'll see the pilot communications channel also being used for things like breaker failure tripping, direct transfer trip channels, things like that. Even though they're considered a separate scheme, they may be leveraging the same communications path as the line differential, because they're accomplishing something similar. You're sending information about what's going on at one terminal to the remote terminal, so it can take action on that. And then lastly, the pilot schemes, they often involve several IEDs, and those would be your relays and communications equipment. And they all need to be specified, designed, and configured uh, consistently between all the terminals to make it work correctly. And that can include carrier equipment, tone sets, multiplexers, um, direct fiber optics. So you have to understand both the fiber themselves and how they're spliced and make sure you're getting the right pairs of fibers between the two stations. And you may have some port adapters and things like that that also have to go into there. So, past just the basic protection requirements of these schemes, there's a lot that goes into the communication side of it that we as protection engineers have to understand in order to be able to make sure the schemes can operate reliably for all possible scenarios. So I've included some additional references on here. A lot of the figures that I used for this presentation I pulled right out of IEEE C37-113, which is the IEEE guide for protective relay applications to transmission lines. Anytime you're looking for any information or references on any kind of protection scheme, the IEEE standards are a great place to start. This one's certainly an excellent resource that goes over in a lot more detail than I did today on these types of schemes, as well as many other considerations that go into transmission line protection. So, as any of you are moving into your careers, I highly recommend familiarizing yourselves with these IEEE standards because they really do have a lot of great information in there. All right, well that wraps up our last day here on transmission line protection. We covered a lot of different topics over the last 4 classes, really looking at both the physical and electrical characteristics of transmission lines, kind of how they play a role in the power system overall, what happens when there's a fault, what measurement quantities and what electrical things can we expect to see at our relays during a faulted scenario versus an unfaulted scenario. We took a look at distance protection and how we can apply impedance-based relaying to reliably protect a transmission line, either with a step distance scheme involving coordination through time delays and sensitivity coordination of the applicable elements, and also took a look today at some other more advanced and complex communication assisted pilot schemes that can offer some improvements over what we're able to accomplish with the step distance schemes just applied locally, primarily in the operate speed and reliability. But that's a trade-off of that is that we're moving from a very simple scheme to something that's much more complex, has a lot of different parts that all have to fit together to apply a reliable protection package. So I hope everybody has learned a little bit about transmission line protection and transmission lines in general from the last few days, and I certainly enjoyed pulling this together and appreciate everybody listening to me over the last few classes. Next time I will be covering a overview of bus protection, and that'll be my last presentation for the course. So I appreciate everybody's time and have a good rest of your day.